how do you check if a physics theory is complete? We need precise measurements. The Muon G-2 experiment at Fermilab in Chicago is an ultra-high precision measurement of the anomalous magnetic moment of muon. Now, how precise are we measuring this anomalous magnetic moment? It's measured to a precision of 127 parts per billion. Now, if you imagine measuring 1 kilometer distance, this is precision of 127 micrometer. So a precision of less than the thickness of your hair. That's how precise the experiment is. Now we are measuring the anomalous magnetic moment of a particle called muon. It's an invisible particle, and in the G-2 ring, it will be going around at the speed of light, that is 3 lakh kilometers per second. And the muon doesn't live that long, it lives for only microseconds. So this high precision experiment has to be done with that tiny amount of time. Now if you take a bar magnet, the magnetism comes from something called electron. It's a tiny invisible particle what makes atom. Now muon is a cousin of electron. It's not around us, but you can produce that in a high energy accelerator. We are measuring the anomalous magnetic moment of the muon, which would be going around at 3 lakh kilometers per second, and the muon lives for only microseconds. So it's an incredibly difficult measurement.
Measuring the anomalous magnetic moment of the muon is extremely crucial for our understanding of the particles and forces that govern the universe. Now for this measurement, the muon has to be traveling very close to the speed of light. That's 3 lakh kilometers per second. The muons are fed into a circular ring which is 45 meters in circumference, and they have to be going around the ring before they decay into other particles such as positrons and neutrinos. Now this ring is not an ordinary ring. It has to have a highly uniform magnetic field of 1.45 Tesla. That's a very high magnetic field. And to get this magnetic field, you cannot use an ordinary magnet. You need a superconducting magnet which is cooled down to minus 270 degrees Celsius using liquid helium. A very large current of around 5,000 amperes goes around in these superconducting coils to create this magnetic field. Now, as these muons decay into positrons and neutrinos, by measuring precisely the magnetic field and the time of decay of the muon, we understand the anomalous magnetic moment of the muon. This fundamentally changes our understanding about the universe. By measuring the magnetic field very precisely and the time of decay of the muon into positrons and neutrinos, we will have the idea of the anomalous magnetic moment of the muon. Now, the Fermilab Muon G-2 experiment has done an incredible job in this ultra precise measurement. Now, we are waiting for the theory to catch up, and let's hope for much more physics to come out of this measurement. The Fermilab Muon G-2 experiment has done an incredible job in this ultra precise measurement. Now, we are waiting from the theory for their precise calculations. Let's hope that this leads to a better understanding of physics for our future.